Before I define exactly what the center of mass is, let me define something called the first and the second moments of mass. And for this purpose, let me take a system of coordinate axes. So let's say we have got xy plane, and of course it might as well be a three-dimensional system where we have x, y, and z axes. So I'm just showing you things in 2 dimensions, but you should keep in mind that they will be easily extended to 3 dimensions. So let's say there is a system of x and y axes, and in this xy plane there are a large number of discrete particles which are placed at different locations. So like this. So all of these are discrete particles which are lying here and there in this xy plane, and I can say that these masses are m1 at a location r1, let us say. Then there is a mass m2 at a location r2. You've got a mass m3 which is at a location r3, and so on. So I can name all these masses, I can figure out how much they are, and I can also figure out where are they with respect to this origin that we have. And to speak about a general mass, maybe I will take a mass mi, the ith particle or the ith mass, whose location with respect to this origin is defined as this ri vector. Now, the first moment of inertia of a mass mi about the origin, about O in this case. So the origin here is a point O, and let me write the first moment of inertia of a mass mi about a point O. And this point O, it can be any point which you choose, and in this example that I have chosen, this point O is the origin. So first moment of inertia of a mass mi about a point O is defined as mi into ri, where this ri will be a vector. So this term which I get will also be a vector. It will be a scaled vector, where ri is the position of mi with respect to this point O, whatever it is. And in our example, O happens to be the origin, but O may have been any other general point also. And because I now know how have we defined the first moment of inertia of a single particle mass mi about a point O, I can define the total first moment of inertia of all these particles about that same point O. So therefore, I can then define first moment of inertia, first moment of inertia of a system of n particles about a point O is defined as summation of I going from 1 to n mi ri, and the answer should be a vector. So please keep in mind that when we define the first moment of inertia of a system of n particles about a point, the answer is expected to be a vector. It is a sum of these individual vectors, where it will be m1 r1 for the first particle, m2 r2 for the second particle, m3 r3 for the first for the third particle, and so on. And based on this same idea, I can now define what is the second moment of inertia. So second moment of inertia is analogous. The only change is that instead of using r vector, it uses r square, the modulus of r vector whole square. So I can define the second moment of inertia, second moment of inertia of a mass mi about a point O is defined as mi ri modulus whole square, which is also mi times ri dot ri. So please keep in mind that it is a dot product of ri and ri, and we can also write that as mi into ri square, and in short we just write mi ri square. We don't put the vector sign and then the mod, we just remove the vector sign and the mod, and we agree to say that if I just write ri, that means it's the modulus of ri vector. And with the help of this I can define the second moment of inertia of all these n particles about this point O. So therefore second moment of inertia of a system of n particle masses or n particles about O is defined as summation of I going from 1 to n mi ri square. So you find out m1 r1 square, you find out m2 r2 square, find out m3 r3 square, and you add up all those terms for all the n particles that you have, and you end up having the second moment of inertia of those system of n particles about this point O. So this is about discrete particle systems. What we have here is a system of n particles, and they are not attached to each other in any fashion. They are discrete, they are individual particles, but this is rarely how we encounter objects in everyday life. The kind of objects that we encounter in everyday life are chairs, tables, vessels, utensils. We have bats and balls, and we have TVs and so on, and all those are made up of a large number of particles which are attached to each other in a certain way. So we should extend this idea to continuous objects. So what will this idea become for continuous objects? So let us say there is a continuous object which is made up of a very large number of particles, and the particles are attached to each other using some kind of intermolecular bonds, and we want to figure out the total first moment of inertia of this object about some point O. The point O may be somewhere. It may be inside the object, it may be outside the object, it may not be the origin. So I'm not going to draw here a coordinate system. I'm just assuming that there is some point O outside here, and I have to find out the first moment of inertia of this entire object about this point O. So the first step will be to break this object into individual chunks. So what I do is I make small portions of, I take small parts, small chunks of this object, and I name each of these chunks as 1, 2, 3, 4 and so on, so that the mass of one of these pieces may become m1, or the mass of this piece may become m1, then you have got m2, and then you have got m3, and then so on. And the piece with the mass m1 is at a location r1, and the one with the mass m2 is at a location r2, and the one with the mass m3 is at a location r3, and so on. So you've got r3 here, you've got r2 here, you've got r1 there, and then for any arbitrary mass piece mi, you've got the location as ri. So you've got this location, this is ri, and you can figure out the total first moment of inertia of this object about this point O by adding up all these individual moments of inertias. And you know that there will be infinite particles, so I will probably say summation of I going from 1 to infinity mi ri. This is the total first moment of inertia of all particles about O. And in the same manner, I can also try to define the total second moment of inertia of all these particles about point O. So you've got total second moment of inertia of all particles about O, and that will be summation of I going from 1 to infinity mi ri square. Now we will see the importance of the second moment of inertia also, but it will come in a later chapter. This chapter is about the first moment of inertia.